somewhere in the darkness beyond our solar system, there is an object smaller than the City of London that could tear a planet apart without ever touching it. It does not have a mouth to consume. It does not have arms to crush. It simply exists, quietly spinning in the black, and that alone is enough to make it one of the most dangerous things the universe has ever produced. Tonight, we are going to explore that object. A neutron star. It sounds almost gentle, doesn't it? Neutron. Star. Two calm words placed side by side. But hidden inside that name is a level of violence that is difficult for the human mind to hold on to. A single teaspoon of this object would outweigh every car, every building, every human being currently alive on Earth combined. Its surface gravity is so overwhelming that if you dropped a marshmallow onto it from a height of 1 meter, the marshmallow would strike the surface with the force of a hydrogen bomb. And that is only the beginning. By the end of tonight's journey, you will understand why astronomers consider neutron stars among the most extreme, most violent, and most genuinely deadly objects that exist anywhere in the cosmos. You will understand how something can be more destructive than a black hole in certain situations, why its magnetic field could erase the data on every hard drive on Earth from 1,000 kilometers away, and why two of these objects colliding somewhere in the ancient universe may be the reason the gold in your jewelry exists at all. But to understand something this extreme, we cannot start with the object itself. We have to start with a death. Every neutron star was once something else. Something enormous. Something that for millions of years lived in a kind of balance so delicate that even a small disruption would end it entirely. Picture a star roughly 10 to 25 times the mass of our Sun. For most of its life, this star is engaged in a quiet tug-of-war. On one side, gravity is constantly trying to crush the star inward, pulling every particle of matter toward the center with relentless, patient force. On the other side, the star's core is generating nuclear fusion, an outward pressure powerful enough to hold gravity at bay. This balance is the only reason stars do not immediately collapse. It is the only reason a star can burn for millions, sometimes billions, of years without imploding. But that balance depends on fuel, and fuel runs out. A massive star spends most of its life fusing hydrogen into helium. When the hydrogen is exhausted, the core contracts, heats up, and begins fusing helium into carbon and oxygen. When that fuel runs low, the process repeats again. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. Each stage burns faster than the one before it, and each stage produces a heavier element. This creates something astronomers sometimes describe as a kind of cosmic onion. Layer after layer of increasingly heavy elements stacked around a shrinking core. But there is a limit to this process. Iron. When a massive star begins fusing silicon into iron, something changes. Iron fusion does not release energy. It consumes it for the first time in the star's life. Nuclear fusion is no longer providing the outward pressure needed to resist gravity. The star's core has essentially run out of moves, and gravity, which has been waiting patiently for millions of years, finally wins. What happens next occurs faster than almost any other event in the universe. The core, which may be roughly the size of Earth, collapses inward to a width of about 20 kilometers in less than a second. Imagine an object the size of a planet compressing down to the size of a city. In the time it takes you to blink, the outer layers of the star, no longer supported, come crashing down onto the newly formed core. They strike it, rebound violently, and the resulting shockwave rips through the star and blasts its outer layers into space in one of the most powerful explosions the universe can produce. This is a supernova. For a brief period, that single exploding star can outshine an entire galaxy of billions of stars combined. But the explosion is not the end of the story. It is the birth of something else. At the very center of that explosion, where the core collapsed, something extraordinary has happened. The crushing force of gravity was so extreme that it did something matter is not supposed to do. It forced electrons and protons to merge together, converting them into neutrons. An object that was once a star's core, filled with atoms and empty space, has been compressed into something almost unimaginably dense. A ball of neutrons packed together with essentially no empty space between them at all. This is the neutron star. And this is where the story gets strange. Here is something worth sitting with for a moment. A neutron star typically contains somewhere between 1 and 2 times the mass of our entire sun, yet it is compressed into a sphere with a diameter of only about 20 kilometers. For comparison, that is roughly the width of a mid-sized city. If you could somehow scoop out a single teaspoon of neutron star material and bring it back to Earth, it would weigh somewhere in the range of 10 million tons. That is heavier than every automobile currently in use in the United States, combined, contained in a space smaller than a sugar cube. The human brain is not built to intuitively process a number like that. So let's try a different comparison. Imagine our sun, an object so large that more than 1 million Earths could fit inside it, being crushed down to the size of a small town. Now imagine that same process happening not gently, but violently, within a matter of seconds. That is roughly what happens during the birth of a neutron star. This is why astronomers often describe neutron stars as the densest objects in the universe that we know of, short of black holes themselves. In fact, a neutron star sits on a razor's edge. A delicate balance between two of the most extreme states matter can exist in. If a neutron star's mass grows too large, roughly beyond 2 to 3 solar masses, not even the intense pressure resisting further collapse can hold the line. Gravity wins one final time, and the neutron star collapses further still into a black hole. Neutron stars, in other words, exist at the very boundary of what matter can survive. They are what is left when the universe pushes a star as far as it can go without crossing over into the complete unknown. It's tempting to think of density as simply a curiosity, an interesting number, a fun fact to share at a dinner party. But density at this scale is not a curiosity. It is a weapon, because mass determines gravity, and a neutron star's gravity is almost beyond comprehension. The surface gravity of a typical neutron star is estimated to be around 200 billion times stronger than the gravity we experience here on Earth. Let's put that into something we can actually picture. If you weigh around 70 kilograms here on Earth, and you were somehow able to stand on the surface of a neutron star without being instantly destroyed, your weight would be equivalent to roughly 14 trillion kilograms. You would weigh more than several fully loaded aircraft carriers. But you would never actually get the chance to stand there. The gravitational pull is so extreme that any object falling toward a neutron star accelerates to an enormous fraction of the speed of light before impact. That marshmallow we mentioned earlier, dropped from just 1 meter above the surface, would strike with a force comparable to a nuclear detonation. Not because the marshmallow itself carries destructive material, but because gravity has accelerated it to such extraordinary speed that the kinetic energy released on impact is almost unimaginable. This single fact reframes how we should think about neutron stars. They are not dangerous because of what they are made of. They are dangerous because of what they do to anything that comes near them. And it turns out, gravity is only the beginning of the danger. To understand how humanity first discovered neutron stars, we have to go back to the 1960s, to a moment that, at first, looked nothing like a scientific breakthrough. In 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope in England, sorting through miles of paper printouts, recording radio signals from deep space. Amid the noise, she noticed something strange. A signal that repeated with an almost impossibly precise rhythm, pulsing once every 1.3 seconds. At first, the team half-jokingly nicknamed the signal LGM-1, short for Little Green Men, because a signal that regular seemed almost too perfect to be natural. Could this be some kind of artificial transmission? Evidence of an intelligent civilization? For a brief period, the possibility could not be ruled out, but as Bell Burnell and her colleagues continued their observations, they discovered more of these strange, rhythmically pulsing signals scattered across different parts of the sky. So, if this had been a message from an alien civilization, it would be an extraordinary coincidence to find several of them broadcasting in almost identical patterns from wildly different directions. The explanation, once it emerged, was almost as strange as the possibility of alien contact. These were not signals from an intelligent species. They were coming from spinning neutron stars. Astronomers named this new class of object a pulsar, short for pulsating radio star. What Bell Burnell had actually discovered was a neutron star spinning so rapidly and emitting such a focused beam of radiation from its magnetic poles that, as it rotated, the beam swept past Earth like the light from a lighthouse. Each time the beam crossed our line of sight, radio telescopes on Earth registered a pulse. The reason the pulses were so mechanically precise was not because they were artificial. It was because neutron stars, once formed, rotate with a stability that puts almost anything else in the universe to shame. And here is where the story becomes genuinely astonishing. Some neutron stars spin not once every 1.3 seconds, like the one Bell Burnell discovered, but hundreds of times per second. Imagine an object with more mass than our Sun, spinning on its axis several hundred times every single second. To understand how that is even physically possible, we need to talk about where that spin comes from in the first place. Before its collapse, the star that eventually becomes a neutron star was already rotating, just as our own Sun rotates slowly on its axis. But that original star might have been over 1 million kilometers across. When the core collapses down to a sphere only 20 kilometers wide, something known as the conservation of angular momentum comes into play. This is the same physical principle that causes a figure skater to spin faster when they pull their arms inward during a routine. A rotating object that shrinks in size without losing its rotational energy must spin faster to conserve that energy. And the neutron star's collapse is not a modest shrinking. It is a reduction in size by a factor of tens of thousands. The result is a rotational speed increase so extreme that some neutron stars, known as millisecond pulsars, spin at rate exceeding 700 rotations per second. At that speed, a point on the star's equator would be moving at a significant fraction of the speed of light. Consider what that actually means physically. An object with more mass than our entire Sun, spinning at over 700 times per second, is held together only by the almost unbreakable strength of neutron degeneracy pressure, a quantum mechanical effect strong enough to resist gravity's crushing force, just enough for the star to survive, rather than collapse entirely into a black hole. If that rotational speed were to somehow increase even further, or if the star's structural integrity were compromised, the outward centrifugal force at the equator could genuinely tear the star apart. Neutron stars, in other words, are not simply crushed. They are crushed and spun at speeds that push the limits of what any physical structure in the known universe can withstand. And this rotational energy, combined with an equally extreme magnetic field, is what creates one of the most genuinely dangerous phenomena in the observable cosmos. Every neutron star possesses a magnetic field. But calling it simply a magnetic field almost undersells what we are talking about. Earth's magnetic field, the one responsible for guiding compass needles and protecting us from dangerous solar radiation, is relatively weak on a cosmic scale. A neutron star's magnetic field, by comparison, can be 1 trillion times stronger than Earth's. To put that in perspective, if a neutron star's magnetic field were somehow relocated to a distance halfway between Earth and the Moon, it would be strong enough to erase the magnetic strip on every credit card on the planet. It could disrupt the data stored on every hard drive, in every computer, every phone, every server, in every home and business on Earth, simultaneously. But even that description falls short of the most extreme members of this family, a special class of neutron star known as a magnetar. Magnetars possess magnetic fields that can reach 1 quadrillion times the strength of Earth's magnetic field. If a magnetar existed at a distance of just 1,000 kilometers from Earth, roughly the distance between two mid-sized cities, its magnetic field would be strong enough to strip the electrons directly out of the atoms in your body. Your body's own chemistry, which depends on atoms holding onto their electrons in stable configurations, would simply cease to function. This would not be a slow, painful process. It would be closer to instantaneous molecular unraveling. We will return to just how catastrophic a nearby magnetar could be a little later in our journey, because the implications reach far beyond simple death. They touch questions about how life could exist anywhere near these objects at all, and why the placement of neutron stars within a galaxy matters more than most people realize. For now, it's worth sitting with this idea. An object smaller than most cities on Earth can generate a magnetic field powerful enough to reach out across 1,000 kilometers of empty space and disassemble matter at the atomic level. That is not science fiction. That is measured, observed physics. We've talked about gravity. We've talked about magnetism. We've talked about rotational speed. But it's worth returning to gravity for a moment, because there is one more layer to this that most documentaries skip entirely. Neutron stars don't just have strong gravity. They have gravity strong enough to visibly bend light around themselves. Because of a neutron star's immense gravitational field, light emitted from the far side of the star, the side facing away from an observer, can actually be bent around the curve of the star and become visible anyway. In effect, if you could safely observe a neutron star up close, you would be able to see more than half of its surface at once, because gravity is curving the light from the hidden side around toward you. This is not a hypothetical prediction. It is something astronomers have modeled using Einstein's general theory of relativity, and it has been supported through observations of how light behaves near these objects. Let that sink in for a moment. The gravity is strong enough to warp the path of light itself, bending it around a solid object the way water bends around a stone in a stream. This single fact tells us something important. Near a neutron star, the ordinary rules that govern how we perceive space, distance, and even light begin to break down. We are no longer dealing with the physics of everyday experience. We are dealing with a location in the universe where Einstein's equations for gravity are pushed close to their breaking point, just one step below the complete extremity of a black hole. And that raises an important question, one that will guide much of where we go from here. If a neutron star can warp light itself, what would actually happen if one entered our solar system? To be clear from the outset, there is no neutron star currently on a collision course with our solar system. The nearest known neutron star to Earth, a pulsar called RxJ856.53754, sits at a distance of a little over 400 light-years away. Even the closest neutron stars are separated from us by such enormous gulfs of space that any immediate threat is essentially non-existent. But that has not stopped astronomers and physicists from asking the question anyway. Because the thought experiment reveals just how extreme these objects truly are. If a neutron star, with roughly 1.5 times the mass of our Sun, were to drift into our solar system and pass anywhere near Earth, the gravitational disruption alone would be catastrophic. Even at a distance of several astronomical units, roughly the space between planets in our solar system, a passing neutron star's gravity would be strong enough to significantly disturb the orbits of every planet. Earth's orbit could be stretched, compressed, or thrown into a wildly different pattern entirely, depending on the exact trajectory. Our planet could be flung out of the habitable zone, sent tumbling toward the Sun, or ejected from the solar system altogether into the frozen dark of interstellar space. And that's before we even consider a closer approach. If a neutron star passed within a distance comparable to that between Earth and the Moon, the tidal forces alone, the difference in gravitational pull between the near side and far side of our planet, would be so extreme that Earth itself could begin to be torn apart. The same tidal forces responsible for ocean tides here on Earth, but multiplied by a factor almost too large to comprehend, would stretch our planet along the line connecting it to the neutron star, potentially ripping it into pieces long before any physical collision occurred. This is one of the reasons astronomers sometimes describe neutron stars as deadly, even without direct contact. Their influence extends outward through space, in the form of gravity and radiation, capable of disrupting or destroying entire planetary systems from significant distances. But there is one specific event, one particular type of encounter, that produces destruction on a scale that dwarfs even this. Two neutron stars colliding with each other, and to understand why that event matters so profoundly, not just for destruction, but for the very existence of certain elements here on Earth, we need to slow down and look closely at what happens when two of the densest objects in the universe finally meet. We'll continue that story shortly, along with a closer look at pulsars, magnetars, and the surprising role neutron stars play in some of astronomy's greatest mysteries. If you find yourself drawn into these strange, quiet corners of the universe the way we are, you're always welcome to like this video and subscribe so you can join us for future journeys through the stranger, more extreme sides of the cosmos. And now, as we look closer at what happens when two neutron stars finally spiral together after millions of years apart, an entirely new kind of violence begins to unfold. Not all neutron stars exist in isolation. Some are born as part of binary systems, two massive stars orbiting a shared center of gravity, locked together from birth. When both stars in such a system eventually go supernova, the result can be two neutron stars, orbiting each other in the emptiness of space, sometimes for millions or even billions of years. At first, this orbit is stable, in the sense that it does not change dramatically from one year to the next. But it is not perfectly stable, not indefinitely. According to Einstein's general theory of relativity, two massive objects orbiting each other lose a small amount of energy over time in the form of gravitational waves, ripples in the fabric of space-time itself. This energy loss is almost imperceptibly small on human timescales. But over millions of years, that gradual, quiet loss of orbital energy causes the two neutron stars to slowly spiral closer and closer together. For most of this process, nothing dramatic appears to happen. The stars simply orbit, gradually tightening their path, decade after decade, millennium after millennium. But eventually, physics accelerates the story dramatically. As the two neutron stars draw closer, their orbital speed increases. What was once an orbit taking days shortens to hours, then minutes, then mere seconds. In the final moments before collision, the two objects can be whipping around each other hundreds of times per second, releasing gravitational waves so powerful that instruments here on Earth, hundreds of light years away, have been able to detect them. And then, finally, after potentially billions of years of separation, they collide. The event that follows is called a kilonova, and it is one of the most energetic and scientifically important events in the known universe. When two neutron stars finally merge, the collision releases an extraordinary burst of energy in the form of gravitational waves, gamma rays, and light across nearly the entire electromagnetic spectrum. For a brief period, the resulting explosion can outshine an entire galaxy. But the significance of this event extends far beyond the explosion itself. For decades, astronomers understood that most of the lighter elements in the universe, hydrogen, helium, carbon, oxygen, are forged inside the cores of ordinary stars through nuclear fusion. Heavier elements, up through iron, are created in the final stages of a massive star's life. But elements heavier than iron, gold, platinum, uranium presented a puzzle. Fusion inside a normal star cannot easily create them, because fusing elements heavier than iron consumes energy rather than releasing it. For a long time, scientists suspected that supernovae alone might account for the creation of these heavy elements. But the numbers never quite worked. Supernovae, as violent as they are, did not appear to produce enough of these heavy elements to account for the observed abundance we see scattered throughout the universe, including here on Earth. The breakthrough came through the study of neutron star collisions. When two neutron stars merge, the extreme densities, temperatures, and neutron-rich material flung outward during the collision create the perfect environment for something called rapid neutron capture, a process in which atomic nuclei absorb neutrons so quickly that they build up into extremely heavy, often unstable elements before they have time to decay. In 2017, astronomers achieved something remarkable. They detected gravitational with neutron-star collision, and for the first time, were able to simultaneously observe the same event using traditional telescopes across the electromagnetic spectrum. This event, known as GW170817, provided direct observational evidence that neutron star collisions produce significant quantities of heavy elements, including gold and platinum. In other words, a meaningful fraction of the gold currently sitting in jewelry, in electronics, in bank vaults, on Earth right now, may trace its origin back to a cataclysmic collision between two neutron stars, an event of unimaginable violence that occurred long before our solar system even existed. This is one of the strange, quiet truths hidden inside modern astrophysics. The most destructive events in the universe are often also the most creative. Without the extraordinary violence of neutron star collisions, some of the heaviest, most valuable elements in the periodic table might not exist here on Earth at all. But the story of neutron star danger does not end with collisions between two of these objects. There is another category of neutron star, one so extreme that astronomers gave it its own separate name and its own separate reputation as potentially the single most magnetically violent object in the observable universe. We are talking, of course, about the magnetar. Earlier, we touched briefly on the staggering magnetic fields produced by magnetars. Now it's time to look more closely at what that actually means, and why some scientists consider a nearby magnetar flare among the most dangerous theoretical threats an inhabited planet could face. A magnetar is a specific type of neutron star with an exceptionally powerful magnetic field generated during its formation through a combination of extremely rapid rotation and complex internal dynamics involving convecting neutron star material. While the exact process is still an active area of research, the resulting magnetic field can reach magnitudes that dwarf even those of ordinary neutron stars. These magnetic fields are so powerful that they physically distort the structure of the star's outer crust. The immense magnetic stress builds up over time, similar to the way tectonic pressure builds along a fault line here on Earth. And just like an earthquake, that stress is eventually released. When it is, the result is called a starquake, a sudden rearrangement of the magnetar's crust that can release an enormous burst of gamma radiation in a fraction of a second. In December 2004, astronomers observed one of the most powerful bursts of energy ever recorded from outside our solar system, originating from a magnetar known as SGR 1806-20, located roughly 50,000 light-years away. In a fraction of a second, this single magnetar released more energy than our Sun produces in approximately 100,000 years. Despite the magnetar being in tens of thousands of light-years away, far outside any realistic danger zone, the burst of gamma radiation was strong enough to measurably affect Earth's upper atmosphere, briefly ionizing portions of it in a manner typically associated with solar flares. This detail is worth pausing on. An event occurring 50,000 light-years away, roughly halfway across our galaxy, was still powerful enough to leave a measurable fingerprint on Earth's atmosphere. Now extend that thought experiment. What would happen if a magnetar flare of similar magnitude occurred not 50,000 light-years away, but merely 10 light-years away, within our own stellar neighborhood. According to research on the topic, a magnetar flare occurring within roughly 10 light-years of Earth could be powerful enough to significantly damage our planet's ozone layer, potentially triggering a mass extinction event. Some researchers have even proposed that a nearby magnetar flare could be a contributing explanation for certain mass extinction events in Earth's ancient history, although this remains a hypothesis rather than a confirmed cause. Fortunately, no known magnetar exists anywhere near that proximity to our solar system. The nearest known magnetars are located thousands of light-years away, well beyond any plausible threat to Earth. But the theoretical danger illustrates something important about neutron stars as a category of object. Their danger is not limited to direct physical contact. A neutron star, and especially a magnetar, can act almost like an invisible weapon, capable of reaching across vast distances of space and disrupting the delicate atmospheric and biological balance of a distant world, without ever moving an inch closer. This is part of what separates neutron stars from almost every other category of celestial object we study. Most dangers in space, asteroids, comets, even black holes at a distance, require relatively close proximity or direct interaction to pose a genuine threat. Neutron stars, through gravity, radiation, and magnetism, can threaten worlds from staggering distances, and this raises a deeper, more unsettling question, one that touches directly on the broader search for life throughout our galaxy. If magnetar flares, gravitational disruptions, and intense radiation fields from neutron stars can threaten planets from such vast distances, how many potentially habitable worlds throughout the galaxy might have already been sterilized or prevented from developing life altogether by the presence of a nearby neutron star? This question does not yet have a definitive answer, but it is one that astrobiologists, scientists who study the potential for life beyond Earth, take seriously when modeling which regions of our galaxy might be safe harbors for life to develop, and which regions might be quietly hostile, shaped by forces too distant and too invisible for us to easily detect. We are going to explore that question in more depth as we continue, because it connects neutron stars to something much larger than physics alone. It connects them to the very question of where and whether life can exist throughout the cosmos. But before we go further outward, there is still more to understand about the neutron stars themselves, particularly the strange behavior happening on and just beneath their surfaces, because it turns out that the surface of a neutron star is not the smooth, simple sphere it might appear to be from a distance. It is instead one of the strangest landscapes that we know to exist anywhere in the universe. If you could somehow observe the surface of a neutron star up close and survive long enough to describe what you were seeing, you would be looking at a landscape unlike anything found anywhere else. The outer crust of a neutron star is believed to be composed of extremely dense, crystallized matter, arranged in a rigid lattice structure. Some physicists have compared it, structurally, to a kind of exotic metal, one far stronger than any material found naturally on Earth. Estimates suggest that the material composing a neutron star's crust may be roughly 10 billion times stronger than steel. Despite this incredible strength, the surface is not perfectly smooth. Neutron stars are believed to have surface irregularities, sometimes described loosely as mountains, although the term is somewhat misleading. Because of the neutron star's immense gravity, these mountains are not tall in any conventional sense. Current models suggest that the tallest surface irregularities on a neutron star might only be a few millimeters in height, held down and flattened by gravitational forces so extreme that anything larger simply cannot exist. And yet, even a millimeter-scale irregularity on the crust of a rapidly spinning neutron star is enough to generate detectable gravitational waves. According to some theoretical models, as the slight asymmetry in the star's shape creates ripples in space-time as it rotates, beneath this crust, conditions become even stranger. Some models suggest the inner layers of a neutron star may contain what is sometimes referred to as nuclear pasta, a term used somewhat playfully by physicists to describe theoretical phases of matter believed to exist under such extreme pressure that atomic nuclei deform into complex shapes, some resembling long strands, others resembling flat sheets, and others resembling more spherical clumps. If confirmed, nuclear pasta may represent the strongest material in the known universe, potentially even stronger than the neutron star's outer crust itself. Even deeper still, at the very core of a neutron star, physicists are not entirely certain what exists. Some theoretical models suggest the core pressure may be extreme enough to break neutrons down further into their constituent quarks, creating an exotic state of matter known as quark matter, a phase of matter not found naturally anywhere else in the observable universe. This means that, in a very real sense, the interior of a neutron star remains one of the last true frontiers of physics. We can observe neutron stars from a distance. We can measure their mass, their rotation, their magnetic fields, and their radiation. But their interior, the actual physical state of matter at those unimaginable pressures, remains a subject of ongoing scientific investigation. In many ways, neutron stars function as natural laboratories, environments where matter is pushed to such extremes that we cannot recreate the same conditions anywhere here on Earth, not even inside our most powerful particle accelerators. Studying them, then, is not simply about understanding a distant exotic object. It is about understanding the fundamental limits of matter itself. What happens when density, pressure, and gravity are pushed as far as the universe allows, right up until the very edge of becoming something else entirely. And that edge, the boundary between neutron star and black hole, is where our journey is about to take us next. Because to fully understand why neutron stars are considered so deadly, we need to understand exactly how close they sit to the most extreme object in the entire universe, and what happens in the strange, uncertain territory between the two. There is a number in astrophysics known as the Tolman-Oppenheimer-Volkoff limit, often shortened to the TOV limit. It represents the maximum possible mass a neutron star can have before its own gravity overwhelms even the extraordinary pressure holding it together. Estimates for this limit generally fall somewhere between 2 and 3 times the mass of our Sun, although the exact value remains an active area of research, partly because it depends on the still uncertain physics of matter at these extreme densities. Below this limit, a neutron star exists in a kind of frozen equilibrium, the outward pressure created by neutron degeneracy, a quantum mechanical effect that essentially prevents neutrons from being squeezed into the same space, is just barely strong enough to resist the inward pull of gravity. Above this limit, that equilibrium fails completely. There is no known force in physics capable of stopping the collapse once a neutron star's mass exceeds this threshold. Gravity simply continues to win, compressing the object further and further, past the point where neutrons themselves can resist, past the point where matter, as we understand, it can exist in any stable form at all. What remains is a black hole. This means that neutron stars occupy a genuinely unique position in the universe. They are the densest form of matter that can exist while still technically remaining matter. One step further, and the object crosses into something fundamentally different, a region of space-time so warped that not even light can escape its pull. Some neutron stars sit dangerously close to this threshold. When a neutron star in a binary system slowly pulls material away from a companion star, a process called accretion, its mass can gradually increase over time. If enough material accumulates, a neutron star that has existed in stable balance for millions of years can suddenly and permanently tip over that edge. Astronomers have observed indirect evidence of this exact process. In some binary systems, a neutron star appears to be slowly gaining mass from a nearby companion, edging closer and closer to the theoretical collapse limit. Whether or when any specific observed system might cross that threshold remains uncertain. But the underlying physics is well understood. Enough additional mass, and the neutron star, one of the densest surviving forms of matter in the universe, ceases to exist as a neutron star at all. This proximity to collapse is part of what makes neutron stars so scientifically fascinating. They allow physicists to study matter under conditions almost identical to those found just outside the event horizon of a black hole. Without needing to study a black hole directly, an object whose interior remains permanently hidden from any form of direct observation. In a sense, a neutron star is what a black hole would look like if the universe allowed us to actually see the extreme physics playing out, rather than hiding it behind an impenetrable boundary. Studying neutron stars gives scientists a rare, indirect window into some of the same physical questions that black holes raise. But with an object we can actually observe, measure, and, in some cases, watch evolve over time. Earlier, we touched on the idea that a nearby magnetar could theoretically sterilize a planet from many light years away. This raises a broader, more fundamental question that astrobiologists have increasingly begun to take seriously. When scientists search for potentially habitable worlds throughout the galaxy, most of the public conversation focuses on relatively familiar concepts. Is the planet in the habitable zone, the region around a star where temperatures could allow liquid water to exist? Does the planet have a rocky composition? Does it have an atmosphere? But there is another layer to habitability that receives far less attention: the safety of a planet's broader neighborhood. A solar system does not exist in isolation. It exists within a galaxy, surrounded by other stars, remnants, and objects, some of which may pose long-term risks that have nothing to do with the star a planet directly orbits. Neutron stars, and especially magnetars, represent one of these hidden risk factors. A planet could orbit a perfectly stable, well-behaved star, sit comfortably within the habitable zone, and still face periodic sterilizing radiation events if a neutron star happens to exist within a certain distance, simply due to random chance in how that region of the galaxy formed. This has led some researchers to propose the concept of a galactic habitable zone, a broader idea suggesting that certain regions of a galaxy may be more conducive to the long-term development of life than others, based not just on the properties of individual stars, but on the density and distribution of dangerous objects like neutron stars, magnetars, and other extreme phenomena throughout that region. Regions closer to the crowded center of a galaxy, where stars are packed more closely together, may face a statistically higher chance of dangerous neutron star encounters or nearby magnetar flares over long timescales. Regions further out, in the quieter, less densely populated outer regions of a galaxy, similar to where our own solar system resides, may offer a statistically safer environment for life to develop and persist over billions of years, undisturbed by these violent, invisible threats. This is one of the quiet, sobering implications of studying neutron stars closely. Their danger is not confined to the specific, rare moments when we might imagine an object like this directly approaching Earth. Their influence through radiation, gravity, and magnetic activity may have played a subtle, long-term role in shaping which regions of our galaxy could support the emergence of complex life at all, and which regions may have been repeatedly, invisibly reset by radiation events long before any life had the chance to fully develop. It is a humbling thought. Our own solar system's relatively quiet, stable position within the Milky Way, far from the more crowded galactic center, and without any nearby neutron stars or magnetars, may be one of the quiet, often overlooked reasons complex life had the opportunity to develop here in the first place. Given how extreme and violent neutron stars are, it might seem like they should be relatively easy to detect, but in reality, finding them presents a significant scientific challenge, precisely because of how small they are. A neutron star, remember, is typically only about 20 kilometers across. On a cosmic scale that is almost unimaginably small, smaller than many cities here on Earth. Combined with the fact that neutron stars do not produce their own light through nuclear fusion, the way ordinary stars do, this makes them notoriously difficult to observe directly. Using conventional optical telescopes, most of what astronomers know about neutron stars comes instead from three primary detection methods. The first, as we discussed earlier with Jocelyn Bell Burnell's discovery, involves detecting pulsars through their regular radio emissions. As a neutron star rotates, if its magnetic field happens to be aligned in a way that sweeps a beam of radiation across Earth's line of sight, radio telescopes can detect this as a remarkably precise, repeating pulse. This method has allowed astronomers to catalogue thousands of pulsars throughout our galaxy. The second method involves detecting X-ray emissions. Neutron stars, especially those in binary systems actively pulling material from a companion star, often produce intense X-radiation, as that infalling material is heated to extreme temperatures before striking the neutron star's surface. Space-based X-ray telescopes positioned above Earth's atmosphere, which would otherwise block these emissions, have been instrumental in identifying neutron stars that might otherwise remain completely invisible. The third, and most recently developed method, involves detecting gravitational waves. As we discussed earlier with the GW 170817 event, when two neutron stars spiral together and eventually merge, they produce ripples in spacetime itself, detectable by extraordinarily sensitive instruments here on Earth, such as the LIGO and Virgo observatories. This method represents one of the newest tools in astrophysics, and it has already provided direct confirmation of processes like heavy element formation through neutron star collisions that were previously understood only theoretically. Each of these methods reveals a different piece of the neutron star puzzle. Radio observations reveal rotation and magnetic field alignment. X-ray observations reveal binary interactions and surface temperature. Gravitational wave observations reveal the final, catastrophic moments of a neutron star's existence, when it merges with a companion. Together, these methods have allowed astronomers to identify thousands of neutron stars throughout our galaxy, and to begin building a genuine understanding of how common and how varied these strange objects truly are. And yet, given how many massive stars have existed and died throughout the history of our galaxy, the neutron stars we have detected likely represent only a small fraction of those that actually exist. Many neutron stars may be positioned in ways that make their radio beams, X-ray emissions, or gravitational signatures difficult or impossible to detect from Earth's current vantage point. Others may simply be too old, too faint, or too quiet to register with our current instruments at all. This means that, scattered throughout our galaxy right now, there are almost certainly neutron stars we have not yet found, quietly spinning in the dark, their extraordinary density and power hidden, simply because their radiation beams happen to point in a direction other than toward us. As astronomers have continued to study neutron stars over the decades since their discovery, it has become clear that they are not a single, uniform category of object. Instead, neutron stars represent a family of related but distinct phenomena, each shaped by slightly different conditions during their formation. We have already discussed pulsars, neutron stars whose rotation and magnetic field alignment produce regular, detectable beams of radiation. And we have discussed magnetars, neutron stars with exceptionally powerful magnetic fields, capable of producing devastating bursts of radiation. But there are other categories as well. Millisecond pulsars represent some of the most rapidly rotating neutron stars known, spinning hundreds of times per second. Interestingly, these are not typically neutron stars that were simply born spinning that fast. In many cases, millisecond pulsars are believed to have been spun up over time by slowly pulling material from a companion star in a binary system, a process that gradually transfers angular momentum to the neutron star, increasing its rotational speed dramatically over millions of years. Binary neutron star systems, as we discussed earlier, represent pairs of neutron stars orbiting each other, slowly spiraling closer together over time, due to gravitational wave emission, eventually resulting in a dramatic merger event. Isolated neutron stars, by contrast, exist alone, without a companion star, drifting through the galaxy after their formation. Some isolated neutron stars appear to have been given a significant kick during the supernova event that created them, propelling them through space at extraordinary velocities. Some of the fastest known neutron stars are believed to be moving through our galaxy at speeds exceeding 1,000 kilometers per second, fast enough to potentially escape our galaxy's gravitational pull, entirely given enough time. This variation reveals something important about neutron stars as a category. While they share the same fundamental origin, the catastrophic collapse of a massive star's core, the specific conditions present during that collapse, the star's original rotation, its magnetic field, its companion star, if any, can produce dramatically different outcomes. In some ways, This mirrors what we understand about snowflakes here on Earth. Every snowflake forms through the same basic physical process: water vapor freezing into ice crystals. And yet, due to the specific atmospheric conditions present during formation, no two snowflakes are ever exactly identical. Neutron stars, in their own extreme cosmic way, follow a similar principle. Same basic process. Wildly different individual outcomes. And this diversity is part of why neutron stars remain such an active area of ongoing astronomical research, more than 50 years after their initial discovery. Every new neutron star observed adds another data point, another piece of evidence, helping scientists refine their understanding of exactly how these extraordinary objects form, evolve, and, eventually, in some cases, meet their own final violent end. We are going to continue exploring that ongoing story, including some of the most extreme individual neutron stars ever discovered, and what they reveal about the true limits of density, gravity, and destruction in our universe. Among the thousands of neutron stars astronomers have catalogued, a small handful stand out even among this already extreme population. Objects that push the boundaries of density, speed, magnetism, and violence further than almost anything else we have observed. Consider PSRJ 1748-2446 AD, currently recognized as the fastest known spinning neutron star, rotating an astonishing 716 times per second. At that rotational speed, a point on the star's equator is estimated to be moving at roughly a quarter of the speed of light. To put that in perspective, if you could somehow paint a single dot on the surface of this neutron star, that dot would circle the star's entire 20-kilometer circumference, more than 700 times in the span of a single second, faster than you could blink your eyes even once. At speeds like this, the neutron star itself is not perfectly spherical. The immense centrifugal force at the equator causes a slight bulging effect, flattening the star very slightly at its poles. Even a small deviation from a perfect sphere, combined with this rotational speed, pushes the star's structural integrity close to its theoretical limits. Some physicists have modeled what would happen if a neutron star's spin rate increased even further. And the results suggest that beyond a certain rotational threshold, the outward force at the equator could genuinely begin to overcome the neutron star's internal cohesion, gradually shedding material outward into space. Then there is SGR 1806-20, the magnetar we discussed earlier, responsible for that extraordinary 2004 gamma-ray burst detected from 50,000 light-years away. Its magnetic field is estimated to be among the strongest of any known object in the observable universe, illustrating just how varied even the most extreme category of neutron star can be. There is also PSRJ 0740-66-2, currently recognized as one of the most massive neutron stars ever measured, with a mass estimated at more than 2 times that of our Sun, compressed into that same impossibly small 20-kilometer sphere. This particular object sits remarkably close to the theoretical TOV limit we discussed earlier, making it an especially valuable subject for physicists, studying exactly how much mass a neutron star can hold before gravity finally wins and forces a collapse into a black hole. And then there is the neutron star at the heart of the Crab Nebula, one of the most well-studied objects of its kind. The supernova that created it was documented by astronomers in China, Japan, and the Arab world in the year 1054. Bright enough to be visible in broad daylight for weeks. Nearly 1,000 years later, the neutron star left behind by that ancient explosion continues to spin roughly 30 times per second, powering the beautiful, expanding nebula of gas and dust that surrounds it. A nebula that has become one of the most photographed and studied objects in the night sky. Each of these individual objects tells a slightly different piece of the larger neutron star story. Together, they illustrate a central truth about this entire category of object, even by the standards of astrophysics, where objects like black holes and quasars already push our imagination to its limits. Neutron stars occupy their own extraordinary category of extremity, a place where matter, gravity, magnetism, and rotation are pushed further than almost anywhere else in the observable universe. We have now explored how neutron stars are born from the death of massive stars, why their density makes them so gravitationally dangerous, how their magnetic fields can act as an invisible weapon across vast distances, what happens when two of them finally collide, and how astronomers first discovered and continue to discover these strange objects scattered throughout our galaxy. But there is still more to this story, because so far we have mostly discussed neutron stars as isolated, individual dangers. What we have not yet fully explored is what happens when a neutron star exists in an active, ongoing relationship with another object nearby, siphoning material, growing and evolving over time. Nor have we explored in depth exactly what would happen, step by step, if a neutron star were to somehow find itself drifting through our own solar system, and how such a catastrophic scenario would actually unfold, minute by minute, if it ever occurred. There is also a deeper question still waiting for us. If neutron stars represent one of the most extreme, most violent categories of object the universe can produce, what does their existence tell us about the broader forces shaping galaxies, star formation, and even the ultimate fate of matter itself across cosmic time? That is where we will pick up next, as we continue deeper into the darkness surrounding these strange, dead stars and the extraordinary physics that governs everything they touch. Not every neutron star lives out its existence in isolation, spinning quietly in the emptiness of space. Some remain gravitationally bound to a companion star, locked in an orbital relationship that can last for millions of years. And in certain configurations, that relationship becomes something closer to a slow, one-sided theft. When a neutron star orbits closely enough to an ordinary star, particularly one that has begun to expand later in its own life, the neutron star's immense gravity can begin pulling material directly off the outer layers of its companion. This process is known as accretion, and it transforms an otherwise quiet neutron star into one of the most energetic objects in the observable sky. As stellar material spirals inward toward the neutron star, it does not fall directly onto the surface in a straight line. Instead, it forms what astronomers call an accretion disk, a swirling, flattened structure of gas, orbiting the neutron star at incredible speed, similar in concept to water spiraling around a drain, but on a scale involving temperatures and velocities that dwarf anything found naturally on Earth. Friction within this disk heats the infalling material to extraordinary temperatures, often exceeding millions of degrees, causing it to glow intensely in X-ray wavelengths. This is precisely how many neutron stars are first identified by astronomers, not through the neutron star's own light, since it produces essentially none, but through the enormous X-ray glow of the material it is actively consuming. Over time, this process does more than simply generate radiation. It gradually transfers both mass and angular momentum onto the neutron star itself. As material spirals inward and eventually strikes the surface, it can cause the neutron star's rotational speed to increase significantly, sometimes dramatically, over the course of millions of years. This is now understood to be the primary mechanism responsible for creating millisecond pulsars, the extraordinarily fast-spinning neutron stars we discussed earlier, capable of rotating hundreds of times per second. Rather than being born spinning at these extreme rates, many millisecond pulsars are believed to be, in essence, recycled neutron stars. Older objects that were originally spinning far more slowly gradually spun up over time through this long, patient process of stealing material from a nearby companion. There is a strange elegance to this idea. A neutron star, already among the most extreme objects the universe produces, does not remain static once formed. It can continue to evolve, sometimes for billions of years, quietly reshaping itself through its ongoing relationship with a companion star, until it eventually becomes something even more extreme than it was at birth. But this process does not continue indefinitely without consequence. As we discussed earlier, there exists a maximum mass a neutron star can hold before gravity finally overwhelms the internal pressure resisting collapse. In some binary systems, astronomers believe ongoing accretion may be slowly pushing certain neutron stars closer and closer to that theoretical limit. If enough material accumulates over time, the outcome is inevitable. The neutron star's internal structure, no matter how resilient, cannot resist gravity forever. At some point, the additional mass tips the balance permanently, and the neutron star collapses into a black hole, disappearing from the observable universe as a distinct object entirely, leaving behind only its gravitational influence and, in some cases, a final brief burst of radiation as the transition occurs. In this way, some neutron stars are not simply passive remnants of stellar death. They are active, evolving objects, capable of consuming their surroundings, transforming themselves, and eventually crossing the final threshold into the most extreme object physics allows. Earlier, we briefly touched on what might happen if a neutron star were to drift into our solar system. It's worth returning to that scenario now, in more detail, because walking through it, step by step, reveals just how completely such an object would reshape everything around it, long before it ever arrived close enough to directly threaten Earth. Imagine, for a moment, a neutron star roughly 1.5 times the mass of our Sun, drifting through interstellar space on a trajectory that happens to intersect with our solar system. Such an object would not announce its approach with any dramatic visual display from a distance. Neutron stars produce very little visible light of their own in the earliest stages of its approach. From many light years away, this neutron star would remain almost completely invisible to observers on Earth, detectable, if at all, only through extremely subtle gravitational influences on the outermost objects in our solar system, distant icy bodies in the Oort cloud, far beyond the orbit of Pluto. As the neutron star continued its approach, drawing closer over the course of thousands of years, its gravitational influence would begin to grow. Long before it came anywhere near Earth, its gravity would begin disturbing the outer solar system, potentially dislodging countless comets and icy bodies from their long, stable orbits, sending some of them tumbling inward toward the inner solar system, and flinging others outward into interstellar space entirely. If the neutron star's trajectory brought it within several astronomical units of the Sun, roughly comparable to passing somewhere near the orbit of Jupiter, the gravitational disruption to the entire solar system would become severe. The neutron star's mass, despite being compressed into an object smaller than a city, exerts the same overall gravitational pull as any other object of similar mass, a star's worth of gravity, concentrated into a source barely 20 kilometers wide, moving through a solar system built around gravitational stability that has held for over 4 billion years. Planetary orbits, including Earth's, would almost certainly be disturbed. Depending on the specific trajectory and closest approach distance, Earth's orbit could be stretched into a far more elongated, unstable path, dramatically altering our planet's distance from the Sun throughout the year, and with it, our climate in ways far more extreme than anything experienced throughout human history. In more severe scenarios, Earth could be gravitationally flung out of the solar system entirely, sent drifting alone into the frozen dark of interstellar space, no longer orbiting any star at all. In other scenarios, Earth's orbit could instead be redirected inward, towards the Sun, with equally catastrophic results. And this is all before considering a genuinely close approach. If the neutron star's path brought it within a distance comparable to that separating Earth and the Moon, the outcome would move beyond orbital disruption into direct planetary destruction. At that proximity, the difference in gravitational pull between the side of Earth facing the neutron star and the side facing away would become so extreme that tidal forces alone could begin to physically tear our planet apart, stretching it first into an elongated shape and eventually fracturing it entirely, long before any direct collision could occur. Fortunately, and this point deserves genuine emphasis, there is no known neutron star anywhere near a trajectory that could bring it close to our solar system, now or in any foreseeable future. The nearest known neutron star remains several hundred light-years away, and the overall population to density of neutron stars throughout our region of the galaxy is low enough that the probability of such an encounter occurring within any meaningful time frame is, for all practical purposes, negligible. But walking through this scenario is not simply an exercise in cosmic horror. It serves a genuine scientific purpose. It illustrates, in concrete terms, just how completely disproportionate a neutron star's destructive potential is relative to its physical size. An object smaller than most cities on Earth, if placed on the wrong trajectory, could unravel an entire solar system that has remained stable for over 4 billion years. Very few other objects in the universe carry that kind of disproportionate danger. Even a black hole of similar mass, while equally capable of gravitational disruption, is at least conceptually more familiar to the public imagination as something dangerous. A neutron star, by contrast, often escapes that same level of public awareness, despite being, in many practical respects, almost equally catastrophic. Among the strangest behaviors observed in neutron stars is a phenomenon known as a pulsar glitch, a sudden, unexpected increase in a neutron star's rotational speed occurring without any obvious external cause. Remember that pulsars are prized by astronomers for their extraordinary rotational precision, some rivaling the stability of atomic clocks here on Earth. This makes it especially notable when a pulsar's rotation suddenly, unexpectedly speeds up, even slightly, before gradually returning to its previous steady rate of rotation or settling into a new steady rate entirely. The leading explanation for this phenomenon connects back to the strange internal structure of neutron stars that we discussed earlier. Beneath the neutron star rigid outer crust, astrophysicists believe there exists a layer of superfluid neutrons, a state of matter that, under these extreme conditions, flows with essentially zero internal friction or resistance. Under normal circumstances, superfluid interior and the rigid outer crust rotate together as a coordinated system. But over time, subtle physical stresses can cause the crust and the interior superfluid to gradually fall out of sync with one another, spinning at very slightly different rates. Eventually, this mismatch reaches a breaking point. In a sudden, dramatic event, the crust and the interior abruptly recouple, transferring angular momentum in a way that causes the neutron star's overall observed rotation to suddenly increase. This is the pulsar glitch. In more extreme cases, particularly involving magnetars, this internal stress can manifest as an actual physical rearrangement of the crust itself. A starquake, similar in basic concept to a tectonic earthquake here on Earth, but involving a crust believed to be roughly 10 billion times stronger than steel. When a starquake occurs on a magnetar, the sudden release of magnetic and structural stress can produce the kind of extraordinarily powerful gamma-ray burst we discussed earlier with SGR 180620, an event powerful enough to be detected from tens of thousands of light years away, and capable, in theory, of significantly affecting a planet's atmosphere from a distance of just a few light years. What makes these glitches and starquakes scientifically valuable, beyond their sheer dramatic power, is what they reveal about the neutron star's otherwise completely hidden internal structure. Because we cannot directly observe the interior of a neutron star, cannot send any instrument capable of surviving such extreme pressure and density, these sudden, observable disruptions in a neutron star's rotation provide one of our only indirect windows into what is actually happening beneath that impossibly dense, impossibly strong crust. Each glitch, each starquake, is in a very real sense a message from the interior of the neutron star, encoded not in light or radio waves directly, but in the subtle timing irregularities of an object that is, under normal circumstances, one of the most precisely predictable clocks in the entire universe. We touched earlier on the detection of gravitational waves from the historic neutron star merger event known as GW170817, observed in 2017. It's worth taking a moment to understand exactly why this detection represented such a profound milestone, not just for the study of neutron stars specifically, but for astronomy as an entire field of science. For nearly the entire history of astronomy, our understanding of the universe has come almost exclusively through observing light. Whether visible light, radio waves, X-rays, or other forms of electromagnetic radiation, every image of a distant galaxy, every measurement of a star's temperature, every observation of a pulsar's radio beam has relied on detecting some form of light traveling across the vast distances of space. Gravitational waves represent something fundamentally different. Rather than being a form of electromagnetic radiation, They are ripples in the very fabric of space-time itself, first predicted by Albert Einstein over a century ago as a consequence of his general theory of relativity, but not directly detected until the year 2015, when the LIGO Observatory recorded gravitational waves produced by a collision between two black holes. The 2017 detection of gravitational waves from a neutron star merger represented something even more significant, because, unlike the black hole collision detected in 2015, this event was also observable through traditional light-based astronomy. Telescopes around the world were able to observe the same event that produced the gravitational wave signal, capturing its optical afterglow, its X-ray emissions, and its gamma-ray burst, all within moments to days of the gravitational wave detection itself. This convergence, observing the same cosmic event through both gravitational waves and traditional electromagnetic radiation, marked the beginning of what astronomers now call multi-messenger astronomy, an entirely new approach to studying the universe that combines multiple, fundamentally different types of cosmic signals to build a far more complete picture of extreme events than either method could achieve on its own. Through this combined observation, astronomers were able to confirm, with direct observational evidence, several things that had previously existed only as theoretical predictions. They confirmed that neutron star mergers produce significant quantities of heavy elements through rapid neutron capture, directly observing the characteristic light signature associated with the radioactive decay of freshly synthesized heavy elements like gold and platinum. They confirmed that gravitational waves travel at the same speed as light, a fundamental prediction of general relativity. By measuring the arrival time difference between the gravitational wave signal and the associated gamma-ray burst, finding them to be almost perfectly simultaneous. It's despite traveling across more than 100 million light-years of space. This single event, a collision between two neutron stars in a galaxy roughly 130 million light-years away, an event that had actually occurred 130 million years before it was detected here on Earth, provided more concrete scientific confirmation about the physics of neutron stars than nearly any single observation before it. It also opened an entirely new avenue for future discovery. Since that first detection, gravitational wave observatories around the world have continued to detect additional neutron star mergers and black hole collisions, gradually building a growing catalogue of these extreme cosmic events. Each new detection adds further data, refining our understanding of exactly how common these mergers are throughout the universe, how much heavy element material they actually produce, and how closely their behavior matches our theoretical predictions. In a sense, the study of neutron stars has become inseparable from some of the most cutting-edge techniques in all of modern astrophysics. What began as a strange, unexplained radio signal detected by a graduate student in 1967 has evolved over the following decades into a central focus of one of the most technologically advanced and scientifically significant fields in the entire discipline. We've already discussed how neutron star collisions appear to be responsible for creating a significant portion of the heaviest elements found throughout the universe, including gold and platinum. But it's worth expanding on exactly how significant this contribution actually is, and what it reveals about the broader chemical history of our galaxy. For most of the 20th century, astronomers generally assumed that supernovae, the explosive deaths of massive stars, were the primary source of heavy elements throughout the universe. This assumption made intuitive sense. Supernovae are extraordinarily powerful, energetic events, and they were already understood to be responsible for creating and distributing many of the elements up through iron. But as astrophysicists developed increasingly detailed models of exactly what happens during a supernova explosion, a discrepancy became apparent. The specific nuclear conditions required to produce very heavy elements through rapid neutron capture. Conditions involving extremely high densities of free neutrons did not appear to be reliably present in standard supernova explosions in sufficient quantity to account for the observed abundance of these elements throughout the galaxy. Neutron star mergers, by contrast, provide almost perfectly ideal conditions for this process. When two neutron stars collide, they eject a portion of their neutron-rich material outward into space at tremendous speed. This ejected material is, quite literally, composed primarily of neutrons, the exact raw ingredient required for rapid neutron capture to occur efficiently, allowing atomic nuclei to absorb neutrons far faster than they can undergo radioactive decay, building up into extremely heavy elements within a time frame of mere seconds. Current astrophysical models suggest that neutron star mergers may be responsible for producing the majority of the universe's supply of elements heavier than iron, including significant portions of the gold, platinum, and uranium found scattered throughout galaxies, including our own. This means that the heavy elements present here on Earth, elements that eventually became part of the rocky material that formed our planet over 4.5 billion years ago, likely originated from a combination of multiple ancient neutron star collisions, events that occurred long before our solar system existed, scattering their newly forged material across the galaxy, where it eventually became incorporated into the vast cloud of gas and dust that would later collapse to form our sun and its surrounding planets. There is something genuinely profound in this realization. The gold in a wedding ring, the platinum in certain electronic components, the trace amounts of uranium powering certain forms of energy generation, all likely trace their ultimate origin back to some of the most violent, destructive events the universe has ever produced. Neutron stars, in other words, occupy a strange dual role in the story of the universe. They represent, in almost every sense we have discussed throughout this documentary, genuine, extreme danger, overwhelming gravity, devastating magnetic fields, catastrophic collisions capable of releasing more energy in a fraction of a second than our sun produces across 100,000 years. And yet, from that same overwhelming violence, some of the most valuable, most enduring materials in the entire universe are born. Destruction and creation, in the story of neutron stars, are not opposites. They are, in a very real sense, the same fundamental process, viewed from two different angles. As extraordinary as our current understanding of neutron stars has become, astronomers and physicists widely agree that significant questions remain unresolved, questions that ongoing and future research efforts are specifically designed to address. One of the most significant unresolved questions concerns the exact physical state of matter. At the very core of a neutron star, the extreme, poorly understood region we touched on earlier, where some models suggest neutrons themselves may break down into their constituent quark particles, forming an exotic state of matter unlike anything else in the known universe. Instruments like NASA's Neutron Star Interior Composition Explorer, an X-ray telescope installed on the International Space Station, specifically to study neutron stars in detail, have been working to measure both the mass and physical size of multiple neutron stars with far greater precision than previously possible. By combining precise mass measurements with precise size measurements, physicists can begin to narrow down exactly which theoretical models of neutron star interior composition are most likely to be accurate, gradually working to resolve one of the most significant open questions remaining in this entire study. Meanwhile, gravitational wave observatories continue to be upgraded and expanded, with future instruments expected to detect neutron star mergers with far greater sensitivity and at far greater distances than current technology allows. Each additional detection adds valuable data, helping refine our understanding of exactly how common these mergers are throughout the universe and how their outcomes vary depending on the specific masses and compositions of the neutron stars involved. Future radio telescope arrays, including large, internationally coordinated projects currently under construction, are expected to dramatically increase the total number of known pulsars throughout our galaxy, potentially allowing astronomers to detect neutron stars in regions of the galaxy that have, until now, remained largely unexplored due to limitations in current telescope sensitivity. There is also continued interest in the theoretical possibility of detecting a hypothetical intermediate object, sometimes referred to as a black hole neutron star transition object, or in searching more directly for evidence of matter existing right at the theoretical boundary between neutron star and black hole, potentially offering direct observational insight into exactly how that final collapse actually unfolds. Each of these ongoing and future research efforts represents a continuation of a story that began quite unexpectedly, with a graduate student sorting through radio telescope printouts in 1967. What started as a strange, unexplained signal has grown, over more than 5 decades, into one of the most active, technologically sophisticated areas of modern astrophysics, involving space-based X-ray telescopes, ground-based gravitational wave observatories, and some of the largest radio telescope arrays ever constructed. And yet, despite all of this progress, neutron stars remain, in many fundamental respects, genuinely mysterious objects. We understand a great deal about their formation, their behavior, their gravitational influence, and their role in producing some of the universe's heaviest elements. But their innermost secrets, the actual physical state of matter existing at their absolute core, remain hidden behind a barrier of density and pressure that no instrument we currently possess can directly penetrate. There is one more chapter to this story, one that surprised even the astronomers who discovered it, and it concerns something almost nobody would expect to find near an object as violent as a neutron star: planets. In 1992, astronomers Alexander Wolszczan and Dale Frail announced a discovery that, at the time, seemed almost contradictory. Orbiting a pulsar known as PSR B1257+12, located roughly 2,300 light-years away, they had detected the telltale gravitational signatures of multiple planets, worlds orbiting not a normal, stable star like our Sun, but the crushed, spinning remnant of a star that had already died in a supernova explosion. This discovery predates the very first confirmed planet, found orbiting a sun-like star, by several years. In other words, the first planets ever confirmed to exist beyond our own solar system were not found around a warm, welcoming star like our own. They were found orbiting one of the most violent objects in the universe, a pulsar spinning rapidly, bathing its surroundings in intense radiation. How could planets possibly exist in such an environment? The leading explanation is almost as dramatic as the discovery itself. Astronomers believe these particular planets are not original survivors from before the supernova explosion that created the pulsar. The violence of that explosion would almost certainly have destroyed any planets that existed beforehand. Instead, these worlds are believed to have formed afterward, condensing out of a disk of debris left behind by the supernova itself, or possibly from material stripped away from a companion star that was gravitationally disrupted during the chaotic aftermath of the stellar collapse. In either case, these are worlds born directly from cosmic destruction, planets that quite literally formed from the wreckage of a star's death, now orbiting silently around the very object responsible for that destruction in the first place. This discovery reframes something important about neutron stars. They are not simply endpoints, final destinations, where matter goes to be crushed, compressed, and rendered dangerous. In certain circumstances, they can also become the unlikely centers of entirely new planetary systems. Systems built from the very material their own violent formation released into space. Whether any of these pulsar planets could ever harbor life is almost certainly out of the question. The intense radiation environment surrounding an active pulsar would make conditions on any orbiting world exceptionally hostile, likely far too hostile to support the kind of complex chemistry believed necessary for life as we understand it. But their mere existence demonstrates something remarkable about the resilience and the strange creative capacity hidden within even the most extreme corners of the universe. Even here, in the shadow of one of the deadliest classes of object known to exist, the universe found a way to build something new. By now, it should be clear that neutron star is not really a single, simple category, but rather a broad classification containing an entire family of related, yet distinct, extreme objects. It's worth pausing to place them side by side, because the differences between them illustrate just how much variation the universe can produce, even while starting from the exact same basic origin, the collapsed core of a massive dying star. At one end of this family sit the ordinary pulsars, neutron stars with magnetic fields powerful by any earthly standard, but relatively modest compared to their more extreme cousins, spinning at rates ranging from roughly once per second to several hundred times per second. Their radio beams sweeping across the galaxy with mechanical precision. At another end sit the magnetars, the true magnetic extremists of this family, capable of the kind of devastating gamma-ray bursts we explored earlier in our journey. Objects whose magnetic fields are so strong they can distort the very structure of their own crust, triggering violent starquakes that release more energy in an instant than most stars produce across enormous stretches of time. Nestled between these extremes are the millisecond pulsars, neutron stars that began their existence as fairly ordinary members of this family, only to be dramatically transformed over millions of years through the slow, patient process of accretion gradually spun up by a companion star until they achieved rotational speeds that push the very limits of what a physical object can withstand without tearing itself apart. There are isolated neutron stars drifting alone through the galaxy, some moving at extraordinary velocities, following the asymmetric supernova explosions that created them, essentially rogue objects with no companion, no orbiting planets, and, in most cases, no easily detectable radiation beam, making them some of the most difficult neutron stars to find at all. And there are the binary neutron star systems, pairs of these objects locked in mutual orbit, slowly losing orbital energy through the emission of gravitational waves, spiraling inevitably closer together across millions of years, until they finally reach the catastrophic conclusion we explored earlier. A merger event capable of forging new gold and platinum, and briefly outshining an entire galaxy. Each of these categories, ordinary pulsars, magnetars, millisecond pulsars, isolated neutron stars, and merging binary systems, represents a different possible outcome branching from that same singular moment of stellar core collapse we discussed at the very beginning of this documentary. The same fundamental process, the crushing of a massive star's core into an object barely 20 kilometers across, can lead to dramatically different final results depending on factors like the original star's rotation rate, its magnetic field, whether it had a companion star, and the specific chaotic dynamics of the supernova explosion itself. This diversity is part of what makes neutron stars such a rich, rewarding subject of ongoing scientific study. They are not a single answer to a single question. They are an entire family of related answers, each one revealing a slightly different facet of what happens when matter is pushed to the absolute edge of what it can physically endure. It's worth pausing here to acknowledge something remarkable about the history of neutron stars, something that often gets lost in the excitement surrounding their eventual discovery in 1967. Neutron stars were not actually a surprise to physics. They were predicted, in a very real sense, more than 3 decades before Jocelyn Bell Burnell ever noticed that strange, repeating radio signal. In 1934, astronomers Walter Baade and Fritz Zwicky, working at the California Institute of Technology, proposed something that, at the time, must have sounded almost like science fiction. They suggested that supernovae, the explosive deaths of massive stars, might leave behind an entirely new category of object, one composed primarily of neutrons, compressed to a density far beyond anything known to exist elsewhere in the universe. At the time this prediction was made, the neutron itself had only been discovered 2 years earlier, in 1932, by physicist James Chadwick. The idea that an entire star's core could collapse into an object made almost entirely of these newly discovered particles was, for its era, an extraordinarily bold theoretical leap based on almost no direct observational evidence at all. For more than 30 years, this remained largely a theoretical curiosity, an interesting idea within the physics community, but one without any confirmed observational support. Many scientists at the time were skeptical that such an extreme object could ever actually be detected, given how small, how faint, and how difficult to observe such a compact, non-luminous object would necessarily be. It was not until 1967, with the discovery of pulsars, that Baade and Zwicky's decades-old prediction finally received direct observational confirmation. The strange, precisely repeating radio signals Bell Burnell had discovered were, in fact, exactly the kind of object theorists had proposed might exist more than 3 decades earlier. This history offers a valuable reminder about how scientific progress often actually unfolds. It is rarely a single, isolated moment of sudden discovery. More often it is a long, patient process spanning decades, involving bold theoretical predictions that sit quietly, sometimes for a generation or more, waiting for observational technology to finally catch up and confirm or refute what theoretical physics had already suggested might be true. Neutron stars, in this sense, represent one of astrophysics' great validating success stories, a case where pure theoretical reasoning, based on the physics of extreme gravity and newly discovered subatomic particles, correctly anticipated the existence of one of the most extraordinary categories of object the universe has ever produced, years before anyone possessed the technology to actually find one. Beyond their raw destructive potential, neutron stars have become something else entirely within the world of physics, an unparalleled natural laboratory for testing the accuracy of Albert Einstein's general theory of relativity under conditions of gravity so extreme that they cannot be replicated anywhere here on Earth. Perhaps the most celebrated example of this involves a remarkable object known as the Hulse-Taylor binary pulsar, discovered in 1974 by physicists Russell Hulse and Joseph Taylor. This system consists of 2 neutron stars orbiting each other closely, one of which is detectable as a pulsar, allowing astronomers to measure its precise rotational timing from Earth with extraordinary accuracy. By carefully tracking subtle changes in this pulsar's timing over an extended period, Hulse and Taylor discovered that the 2 neutron stars were gradually spiraling closer together, losing orbital energy at a rate that matched, with remarkable precision, the predictions of Einstein's general theory of relativity regarding the emission of gravitational waves. This discovery provided the first indirect evidence that gravitational waves actually exist, decades before they were finally detected directly in 2015. For this achievement, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993, a testament to just how significant this particular neutron star system proved to be for advancing our fundamental understanding of gravity itself. An even more extraordinary system was discovered in 2003, a genuine double pulsar, officially designated PSR J07373039, in which both neutron stars in the binary system are detectable as pulsars from Earth. This exceptionally rare configuration has allowed physicists to test multiple, distinct predictions of general relativity simultaneously, using the precise, mechanically reliable timing of 2 separate pulsars orbiting each other at extraordinary speed. Through detailed study of this double pulsar system, physicists have been able to measure effects predicted by general relativity with a level of precision that rivals, and in some cases exceeds, any other test of Einstein's theory ever conducted, including tests performed using highly sophisticated laboratory equipment here on Earth. This is part of what makes neutron stars so valuable to physics. Beyond their inherent dramatic danger, they exist at gravitational extremes that no human-built laboratory can replicate, providing scientists with a genuine, real-world testing ground for some of the most fundamental theories governing how the universe actually operates. Each new neutron star system discovered particularly binary systems involving two of these extreme objects, offers another opportunity to test, refine, and so far, consistently confirm the remarkable accuracy of a theory first proposed by Einstein over a century ago. To fully appreciate exactly how extreme neutron stars truly are, it helps to place them alongside the other possible endpoints of stellar evolution, because not every dying star produces an object of this kind. The specific fate awaiting any given star depends primarily on its mass. Stars with a mass similar to our own Sun, roughly up to about 8 times the Sun's mass, do not undergo the kind of catastrophic core collapse we described at the beginning of this documentary. Instead, after exhausting their nuclear fuel, these smaller stars gradually shed their outer layers into space, forming a glowing shell of gas known as a planetary nebula, while their core settles into a considerably less extreme, though still remarkably dense, object known as a white dwarf. A white dwarf, while dense by ordinary standards, is nowhere near as extreme as a neutron star. A typical white dwarf might compress roughly the mass of our Sun into an object approximately the size of Earth. Dense, but still enormously larger and enormously less gravitationally extreme than the 20-kilometer sphere of a neutron star. Stars with significantly greater mass, roughly between 8 and 25 times the mass of our Sun, are the stars that produce neutron stars. Following the dramatic core collapse supernova process we explored at the very beginning of this documentary, and stars with even greater mass still, generally exceeding roughly 25 times the mass of our Sun, may undergo a core collapse so extreme that not even neutron degeneracy pressure can halt it. In these cases, the collapsing core continues compressing past the point where a neutron star can stably exist, continuing all the way down into a black hole, an object so gravitationally extreme that not even light itself can escape its pull. This progression, white dwarf, neutron star, black hole, represents, in a very real sense, an ascending ladder of gravitational extremity, each step representing a state of matter compressed further and held together by increasingly desperate and increasingly extreme physical forces, until finally, at the level of the black hole, no known force in the universe remains capable of resisting gravity's pull at all. Neutron stars occupy a particularly fascinating position on this ladder. They represent the absolute final rung, the very last stop before matter as we understand it ceases to exist as matter altogether. Beyond the neutron star, physics as currently understood simply runs out of answers, and the object continues collapsing toward a singularity, a theoretical point of infinite density that remains, even after more than a century of study, one of the greatest unresolved mysteries in all of physics. Understanding neutron stars, then, is not simply about understanding one interesting category of object among many. It is about understanding the very edge of what matter is capable of enduring, the final, observable boundary before the universe's physics becomes something we currently have no complete framework to describe at all. Throughout this documentary, we have relied heavily on numbers, comparisons, and physical descriptions to convey just how extreme neutron stars truly are. But numbers alone can only carry us so far. It is worth taking a moment to simply imagine as vividly as the human mind allows what an encounter with one of these objects might actually feel like if such a thing were somehow survivable long enough to perceive. Approaching a neutron star from a great distance, the first thing you might notice is not the object itself, but its effect on the light passing near it. Stars behind the neutron star, from your perspective, would appear distorted, smeared into strange, curved arcs of light, bent around the neutron star's gravity in a way that has no equivalent anywhere in ordinary human experience. This is gravitational lensing, the same phenomenon that allows astronomers to see slightly more than half of a neutron star's surface at once. And up close, it would transform the surrounding starfield into something closer to a living, shifting piece of abstract art than the fixed, familiar night sky most of us know. As you drew closer, gravitational time dilation, another consequence of Einstein's general relativity, would begin to take effect. Time itself would begin passing at a measurably different rate for you than for a distant observer watching from far away. This is not a hypothetical curiosity. It is a real, measurable effect that has been factored into precise timing calculations for pulsar observations, and it becomes increasingly pronounced the closer one approaches an object of such extreme mass and density. If you continued your approach, tidal forces would begin to assert themselves long before you reach the surface. The gravitational pull on the side of your body closest to the neutron star would become measurably, then dramatically, stronger than the pull on the side facing away. This differential force, if experienced by an actual human body, would result in a process astrophysicists somewhat grimly refer to as spaghettification, a gradual, then increasingly rapid, stretching of matter into long, thin strands, a fate more commonly associated with black holes, but equally applicable to a close approach toward a neutron star, long before any physical contact with the surface occurred. An approaching object, whether a spacecraft, an asteroid, or, in this thought experiment, a human observer, would already have been torn apart entirely by these extreme tidal forces, its constituent matter stretched, shredded, and ultimately consumed by the neutron star's overwhelming gravitational field. This thought experiment, while obviously impossible to survive, serves an important purpose. It transforms the abstract numbers we've discussed throughout this documentary, 200 billion times Earth's gravity, a magnetic field a quadrillion times stronger than our planet's, into something closer to a genuine felt sense of scale. Neutron stars do not merely possess extreme properties in some distant academic sense. They represent environments so fundamentally hostile to any structure resembling ordinary matter that survival, in any meaningful sense, becomes physically impossible long before actual contact could ever occur. There is one final piece of the neutron star story worth exploring before we bring our journey to a close, one that connects these extreme objects to a phenomenon that occasionally, and quite literally, rains down upon Earth from space. Cosmic rays, extremely high-energy particles that travel through space at velocities approaching the speed of light, have puzzled astronomers since their discovery in the early 20th century. While the Sun produces lower-energy cosmic rays on a regular basis, the very highest energy cosmic rays ever detected carry energy levels that seem almost impossible to produce through any conventional astrophysical process. Neutron stars, and particularly magnetars, have emerged as one of the leading candidate sources for at least a portion of these extraordinarily high-energy particles. The combination of extreme magnetic fields and rapid rotation found in these objects can, according to current theoretical models, act as a kind of natural particle accelerator, flinging charged particles outward at velocities and energies that would require facilities far more powerful than any particle accelerator ever constructed here on Earth, including the Large Hadron Collider, currently the most powerful such machine humanity has ever built. If this theoretical connection is correct, it means that at least some of the cosmic ray particles that occasionally strike Earth's upper atmosphere, and, in rare cases, are even believed to have influenced biological mutation rates over the deep history of life on our planet, may have originated from the magnetic fields of distant neutron stars, flung across the galaxy over thousands or even millions of years before finally arriving here. This represents yet another way in which neutron stars, despite existing at almost incomprehensible distances from Earth, maintain a subtle, ongoing connection to events occurring here on our own planet. Their influence is not confined solely to the dramatic hypothetical scenarios we explored earlier. A neutron star drifting through our solar system, or a magnetar flare sterilizing a nearby world in smaller, quieter, but continuous ways. The physics occurring within and around neutron stars scattered throughout our galaxy may already be leaving faint, measurable fingerprints on Earth, arriving as individual high-energy particles, invisible to the naked eye, yet occasionally significant enough to influence the very molecular biology of life itself. It is a fitting final reminder of something that has run throughout this entire documentary. Neutron stars may exist at staggering, almost unimaginable distances from our own small, quiet corner of the galaxy, but their influence, through gravity, through radiation, through magnetism, and through the particles they fling outward across the vast emptiness of space, reaches far further and far more persistently than their tiny 20-kilometer size might ever suggest. There is a final, unexpected twist to this story, one that transforms neutron stars from purely objects of danger and scientific curiosity into something almost practical, almost useful, in a way that connects directly back to humanity's own tentative first steps beyond our solar system. In 1972 and 1973, NASA launched the Pioneer 10 and Pioneer 11 spacecraft, each carrying a small, golden plaque designed to communicate basic information about humanity and the location of Earth in the unlikely event either spacecraft was ever encountered by an intelligent civilization somewhere in the depths of interstellar space. Designing this plaque presented an unusual challenge. How do you describe your location within an entire galaxy, using a medium that assumes absolutely no shared language, no shared units of measurement, and no shared cultural reference points with whoever might eventually find it? The solution the mission's designers settled on involved pulsars. Because pulsars rotate with such remarkable near-atomic clock precision, and because each individual pulsar's specific rotational period is essentially a unique cosmic fingerprint, the Pioneer plaque included a diagram depicting the precise rotational periods of 14 specific pulsars, each shown radiating outward from a central point representing our Sun. In theory, any sufficiently advanced civilization capable of intercepting the spacecraft would also be capable of independently identifying these same 14 pulsars from their own location within the galaxy, using their unique, unmistakable rotational timing as a kind of cosmic address, allowing them to triangulate the exact location of our solar system, even without any shared written language. This same fundamental idea, using the extraordinary rotational precision of pulsars as a kind of natural, galaxy-wide navigational beacon, has continued to develop well beyond this early, largely symbolic gesture. In recent years, scientists have begun seriously exploring the concept of pulsar-based navigation for actual future interstellar or deep space missions. Because certain pulsars maintain such extraordinarily stable, predictable rotational periods, a spacecraft equipped with instruments capable of detecting their X-ray or radio emissions could, in principle, determine its own precise position and velocity anywhere within the galaxy, without needing to rely on communication with Earth at all. This would function somewhat similarly to how GPS satellites allow navigation here on Earth, except using naturally occurring pulsars scattered throughout the galaxy instead of artificial, human-built satellites. In 2017, NASA successfully tested a proof-of-concept version of this technology aboard the International Space Station using an instrument to detect X-ray emissions from several known pulsars and successfully calculate the station's position in orbit, using pulsar timing data alone, demonstrating that this once purely theoretical navigation method could genuinely function in practice. There is something quietly remarkable in this development. The very same objects capable of the kind of overwhelming, near incomprehensible destruction we have spent most of this documentary exploring. Crushing gravity, devastating magnetic fields, catastrophic collisions capable of outshining entire galaxies, also happen to possess a rotational stability so extraordinarily precise that humanity has begun seriously considering using them as permanent, reliable navigational reference points for future deep space exploration. In a sense, neutron stars offer humanity something few other objects in the universe can: a fixed, dependable point of reference, scattered generously throughout our galaxy, remaining stable and predictable across time scales far longer than any human civilization has yet existed. Even as they represent one of the most violent, unpredictable categories of destructive force found anywhere in the cosmos, their underlying rotational behavior remains, paradoxically, among the most reliable, most trustworthy phenomena available to us. Perhaps this is fitting, as humanity continues its own slow, careful expansion outward from Earth, first with robotic probes, and perhaps, eventually, with human travelers venturing beyond our own solar system. We may find ourselves relying, in a very literal, practical sense, on the precise, silent, unwavering rotation of the same objects, capable of unraveling an entire planetary system, should we ever be unfortunate enough to encounter one too closely. The universe, it seems, rarely divides its phenomena neatly into categories of purely helpful or purely dangerous. Neutron stars exist as both, simultaneously, depending entirely on distance, circumstance, and the particular way in which humanity chooses to observe and interact with them. Throughout this documentary, we have focused largely on danger, overwhelming gravity capable of unraveling a solar system, magnetic fields powerful enough to strip electrons directly from atoms, collisions releasing more energy in an instant than our sun produces across entire geological epochs. And all of this is, by any reasonable measure, entirely accurate. Neutron stars genuinely are among the most extreme, most potentially destructive objects that exist anywhere in the known universe. But there is another way to understand these objects, one that shifts the emotional weight of everything we've explored tonight. Every neutron star we have discussed, every pulsar precisely timing out its rotation across thousands of light years, every magnetar with its almost incomprehensible magnetic field, every collision that forged the gold now sitting quietly in jewelry boxes and bank vaults here on Earth, exists because a star, somewhere, at some point in the deep history of our galaxy, lived out its entire life and eventually died. A neutron star is not simply a dangerous object floating in space. It is a gravestone, a final, physical record of a star that once shone brightly enough to be seen across vast interstellar distances, that fused hydrogen into helium for millions of years, that eventually exhausted its fuel, collapsed, and in one final, spectacular act, gave rise to the very elements that would later become part of new stars, new planets, and, in at least one known case, new life. When we look up at the night sky and consider that scattered throughout our galaxy are the crushed, compressed remains of massive stars, spinning in the dark, some slowly, some hundreds of times per second, we are looking at a kind of cosmic history written directly into the fabric of the universe itself. Each neutron star represents a specific, individual death and, indirectly, a specific, individual contribution to the ongoing chemical evolution of our galaxy. The iron in human blood, astronomers remind us, was forged in the final moments of a massive star's life. The calcium in human bones was formed through nuclear fusion processes occurring deep within ancient stellar cores. And now we understand that at least some portion of the heaviest elements present here on Earth, elements that have found their way into human technology, human art, and human culture, trace their origin back specifically to the collision of two neutron stars, an event of almost unimaginable violence occurring somewhere in the ancient universe, long before our Sun, our Earth, or any form of life as we understand it, had ever come into existence. There is a particular kind of humility available in that realization. The most extreme, most dangerous objects we have discussed throughout this entire documentary are, at the same time, directly responsible for some of the material that eventually became part of our own bodies, our own planet, and our own civilization. Danger and creation, violence and origin, destruction and continuation. These are not separate, unrelated concepts in the story of neutron stars. They are, quite literally, two descriptions of the exact same underlying physical process, viewed across different scales of time and consequence. We began this documentary with a simple, direct question. Why are neutron stars considered among the deadliest objects in the entire universe by now? That question has, in a very real sense, been answered. Their density creates gravity strong enough to reduce a falling marshmallow to the destructive equivalent of a nuclear detonation. Their magnetic fields, in the most extreme cases, are powerful enough to strip electrons directly from atoms across a distance of 1,000 kilometers. Their collisions release more energy in a fraction of a second than our Sun produces across 100,000 years. And their gravitational influence, if one were ever to drift too close to a planetary system, could unravel orbital stability that has held steady for billions of years. By any reasonable definition, neutron stars have earned their reputation as some of the most extreme, most genuinely dangerous objects that exist anywhere in the observable cosmos. And yet, as is so often the case with the deepest questions in astrophysics, Resolving one central mystery has revealed several new ones in its place. We still do not fully understand the exact physical state of matter existing at a neutron star's absolute core. We still do not know with complete certainty exactly what triggers the specific magnetic field strength that determines whether a given neutron star becomes an ordinary pulsar or an extreme magnetar. We do not yet know exactly how many neutron stars exist scattered throughout our galaxy, hidden from detection, simply because their radiation beams happen to point in directions other than toward Earth. And we do not yet know, with complete confidence, exactly how close a neutron star or magnetar would need to approach before its radiation could meaningfully threaten a planet's habitability, a question with implications reaching far beyond our own solar system. Into the broader search for potentially habitable worlds scattered throughout our galaxy. Perhaps most significantly, we still do not have direct observational access to the singular moment when a neutron star's mass finally exceeds its theoretical limit and it collapses into a black hole. This transition, one of the most extreme events physics allows, remains something we can model mathematically, but have never directly observed occurring in real time. Each of these open questions represents an active area of ongoing scientific investigation, a genuine, unresolved frontier at the edge of what humanity currently understands about the universe. And perhaps that is the most fitting way to end our journey through the world of neutron stars, not with a tidy, fully resolved conclusion, but with a clear-eyed understanding of exactly how much has been learned, alongside an honest acknowledgement of exactly how much remains hidden, waiting somewhere out in the dark, spinning quietly within objects smaller than most of Earth's cities, holding secrets that may take decades or longer for humanity to finally uncover. Somewhere out there, right now, a neutron star is spinning, hundreds of times each second, its beam of radiation sweeping silently across the galaxy, utterly indifferent to whether anyone is watching. Somewhere out there, two neutron stars are slowly spiraling closer together, locked in an orbital dance that will not conclude for millions of years, building toward a final, catastrophic collision that will eventually forge new gold, new platinum, new elements destined to one day become part of some future star, some future planet, perhaps even some future form of life we cannot yet imagine. And somewhere out there, quietly, patiently, the universe continues doing what it has always done, taking the violent, catastrophic death of one thing and using it, slowly, methodically, to build the raw material for something entirely new. That is the story of the neutron star. Not simply an object to fear, though it has certainly earned that reputation, but also, in its own strange, extreme way, a quiet, essential architect of everything that came after it, including, perhaps, us.